like talk about this. There was a lot of research on a few things that about spalling and the factors that are involved. Um, there's what I really would like to do is kind of just debunk some of those. And what Maddie was talking about was most of the science, and then here I would like to talk about the applications. So first, there's a lot of applicable codes that you may use. I know we use 921 as a guidance for the forensics, but I was doing a literature review of like different NFPA as well as like other codes. So this is just to build somewhat of a procedure of maybe how you would analyze spalling. But just like as I said, it's a very complicated topic and involves a lot of factors. But here I would just like to focus mostly on how to relate like the density as well as like the temperature. And just to be careful, which I'll reiterate in a little bit, but if we take into account permeability and water cement ratio, that can really alter if you are gonna get some spalling or not. So I'll talk about that more in a bit. But what you see here is the codes and tests that I use, and these are just references of where I got the properties as well as some of the procedures that I want to talk about. But mainly, the first thing I did is gather standard room dimensions and standard fuel orientation. For this one, I believe I used the NFPA 86, not for the test itself. I kind of altered the fuel dimensions, but just to serve as an example of how you would apply this. And then I also use the IBC just to get some relative dimensions for the slab and the wall. And then for the concrete properties, I use ACI 216 and 318. And then for the thermal and how to create the curves, I use, we've done this a lot, but we technically kind of followed the Eurocode 1 and 2. And then we use that as like what we input into our analyses. And then to serve as a like how you would know if spalling did occur, there's two things that some codes have used, but there's this one, the NFPA 502. But this is, I've read some of these, but these are applied mostly for tunnels and bridges. And then I guess I was looking at like SFPE for if there's one that's applied for a building. And there are, and then some of these values, they vary from 380 to like 400 Celsius. So I just use the conservative value of 380. So that's what you're gonna see. And then I guess to provide as a test, so this is gonna be the simulation and provide as a test in the field. It's actually a good transition to the next slide. Is this ASTM C856. This is just like one test that you can use to see the extent of spalling. What you see here is just a sample. So for example, you have a case where maybe there was a spalling of an element, a beam or a column, and then you want to see the extent of the spalling. This is one thing that you may use just to explain. This is kind of like a color image analysis. So what this petrographic test is just just an observation test. You can use this. One of the analyses you can use is a color image test. So what I found out was there's actually this critical temperature for concrete, and I think everyone knows this, but then there's concrete and then the steel inside the concrete. But so it affects them both separately. For concrete itself, since it has a lot of resistance, lower conductivity, you're gonna get a higher temperature here at 380, as I mentioned. And then for the rebar, maybe an earlier temperature, 250. So how you would use this out in the field is, so you would break that element out and then you would observe the color configuration that you see in the cross section. So for example, if you see a lot of pink and red, that's really an indication of if spalling occurred. And I've read this in literature as well. And then the higher you go in temperature, this buff and then black grayish color is what you're going to see. So just to so that this is the test, and then it'll be a good way to confirm with the simulations as well as a field test of if you actually get any spalling. So just to cover a few things, this is just a simulation that I did, a model to develop if you were to query a spalling element. So just to explain briefly, the first model is a low density concrete, and then the second model is a high density concrete. And Maddie kind of spoke to this about the differences in the densities and how it changes the temperature. So just to cover what this sample simulation is going to do is, so we have an office type building, group B, and then I just chose maybe like a type 1B, non-combustible. And then I looked up, you know, that's 2 hours. So that's what we typically use depending on the material. And then for the size of the compartment, this is from 286. And then the ventilation, you're gonna see this in a bit, but I just use like the 1 door ventilation, and then the burner size. And then for slab thickness and wall thicknesses, I use the minimum. So from those references I got, if you wanted to get a 2-hour resistance, minimum, obviously this in the field is going to be larger than this, but the slab on the wall may be about 3.6 inches. And then we want to be consistent, so I just made this all a metric. And then for both of those, I got like what their thermal properties are. And then next, so I also got the material properties. And then for the fuel, I just use a polyurethane sofa. So this can be changed depending on what scenario you have, and then the fire size. And then from that, this might be new, but what we typically do is we would use the Eurocode just to get this density, the design fire load, and that it really depends on the size of the compartment and that you have, and the occupancy, and whether you had like you took into account firefighting measures. And then so those are the factors: surface factor, which depends on your the thermal properties, and then opening factor, which depends on your ventilation and then the enclosure areas, and then the temperatures that I use as a benchmark. So here's the FDS model that I use. I think we use this in FP 504. So that's why I use it as a sample, because everyone's familiar with it. So, but then what I used differently was the liners, or the type of material we use here. So I just use like these as concrete, slab, and walls. And just to show you guys, so remember, I'm trying to compare the different densities and how they affect the thermal response and then the structural response. So for lower density concrete model, that'll be model 1. This is the simulation that I did. Okay. So yeah, so as you can see, the corner, the black ring, I made that as like the average temperature. I think here is about 468 Celsius. And then this is our structural response. So this is just a section of maybe a wall, a 1-foot section of a wall, or of a ceiling or floor. So here's the thickness, I think the 3.6, and then here's 1 foot. And then the different colors represent the thermal gradient. So what you see here is you have the concrete. It's about 400 C, but you're gonna see it's about, I think from the FDS it was 468. And then the reinforcing steel, so I just used these minimal, about 262 for our low density model. And then the next one is the high density. So what I did here, it's exactly the same model, but just the thermal properties are different, as well as the concrete properties. So the same thing, this black ring, it's about 277 is the average temperature. And then so this model was a little different for the structure response. The properties I used was for high strength concrete, and then that's what I'm going to talk about in a bit. Is high strength concrete that really has, even though the temperatures show that you're not going to reach like spalling conditions, in literature it says that once you do reach spalling, it does have a lot of explosive. It's a very brittle material, so your spalling is going to be very volatile. So in a sense, the reason why it's more prone for, here, I'll show you the results. But for high density concrete and in low density concrete, you're gonna have these different temperatures, and that's from the different locations that I measured, from the wall, the ceiling, and then this is from the FDS, and then these are from the program for the structural response, the concrete, and then the steel. And so what you see here is, so this equation we know, and this is just the ignition equation for thermally thick. And how I'm applying this is the relationship between the thermal inertia and then the temperature, keeping these consistent. And so as you see from these temperatures, the lower your density, the greater temperatures you get. And then comparing that to the spalling criteria, you're gonna get these to spall. And then for a higher density, your temperatures decrease because of this equation. And then you're probably not gonna get spalling. But as I mentioned here, is the lower your permeability, if you take into that account, and then your water cement ratio, then you're gonna get a greater tendency to spalling. And then because you have a brittle material, there's less moisture in your cross section. So with that, maybe how we can apply this to forensics is the building information. Maybe the inputs are different. Building information you obtain, the factors that I mentioned, the fire load density, surface factor, opening factor, and then just, I guess we talked about standard fire curves, but we've used this before, the parametric fire curves. This just takes into account the heating and the cooling phases, and then if we're spalling, it does lose strength, not only in the heating but also in the cooling phase. And for different fuel packages, this changes, maybe depending on your case, the size and the duration. And then for the ignited material, maybe your geometric properties and material properties will change. So this is just what I think. Maybe you can use simulations to inform whether you do get spalling, and maybe you can use tests to, like as I mentioned before, to see the extent of how far you get, or how far your element spalled. So just to end with this, we wanted to show you guys a spalling demo. This is from a company, Effectus, a European company. They're kind of similar to here what Intertech would do, where they would test your, or it would conduct fire tests, and then they also do modeling. So just to show this. Just over there. So as you increase this, you're gonna see the software here, spall. Okay. All right, so that's pretty much what we have.